Yeah, welcome everyone. Thank you for coming together. Causal Inference is very much moving online lately. There's also the online Causal Inference seminar that you guys should check out if you don't know what that is. It's every Tuesday. It's my distinct pleasure to introduce Rohit, Bhattacharya, and Razieh and Nabi, who are both working with me. Razieh was actually my first student after I got to Hopkins, and Rohit sort of joined my lab after working on cancer genomics for a while. They both are amazing and have already taught me a lot. I think we've gotten to the point where I don't really teach them, they teach me. They both have done seminal work in all sorts of areas of causal inference and mediation analysis and missing data and algorithmic fairness and interference and structural learning and semiparametric statistics. And that's what they are going to be talking about today. And their talk will be about deriving semiparametric inference estimators for causal effects where, how shall we say, we don't really have conditional ignorability anymore, and life is more complicated and you have all sorts of hidden variables everywhere. And as a consequence, your identifying functional is complicated. So please, Rohit and Razieh, take it away.
All right. Thanks, Ilya, for the introduction. And thanks, everyone, for tuning in. I hope you all are staying sane and healthy. So the first half is on me. But before I start, I wanted to give a shout out to Dan Charleston for his semi-parametric reading group that he ran last year. So we really learned a lot from him. And just thanks. And so I'm just going to jump right into it. So to motivate our talk, let's say we are interested in quantifying the effectiveness of competing antiretroviral treatments with varying levels of toxicity on CD4 counts in HIV-positive patients. And let's say we have access, there is a reason that we believe that we have access to all the common confounders between the treatment and the outcome. So this situation is illustrated in this graph. It's known as the conditional ignorable model, meaning that conditional the confounders, the treatment is behaving as if it was randomized. But really, we can't make a strong case for conditional ignorability because there might be unmeasured confounders that we are missing, especially if you are working in with observational data. So here in this graph, we are interested in the effect of the treatment on outcome. And because of this unmeasured common confounder or hidden variable, the effect of T on Y is not identified without making any further assumptions. But let's say we believe that there is a mediator that we measured that captures, that mediates all the effect of the treatment on outcome, and it doesn't have any unmeasured causes. So for example, one potential mediator could be toxicity level and chemical reaction to the treatment. So this graph, some people may recognize this as front door graph, and the effect of T on Y is indeed identified in this graph. But maybe this graph is too simplistic for you guys, and maybe you think that toxicity actually leads to differential adherence, and differential adherence affects the CD4 count. And maybe you think that there is the relation between the observed variables and the hidden variables are more subtle. Like for example, there is unmeasured confounders between the treatment and the adherence, and there are unmeasured confounders between the mediator, between the toxicity and the outcome. So we can go on and make bigger and bigger graphs. But the good news is in this graph is still the effect of T on Y is identified. So what the thing is, there exists a sound and complete algorithm that tells us when and how the effect of T on Y is identified. So this algorithm was developed by Jin Tian, and it was proved to be complete by Ilya and on an independent work by Huang and Valtorta. And it's been condensed enough by Ilya that we just call it one-line ID. So the nice thing about it is that if you draw your story in a form of a graph, and the algorithm is just going to tell you if the effect is identified or not. And if it is identified, it's going to spits out an identified function of the observed data without relying on any parametric assumptions about your data generating process. That's why it's called a non-parametric identification. But really the truth about one-line ID is that it's not really tailored for estimation purposes. And oftentimes the functional that the one-line ID outputs is very complicated, and it unnecessarily relies on a big portion of the joint distribution. So it makes it very hard in finite samples to estimate the effect. And shockingly, there's been very few work in this area of doing like estimation for the functionals that the ball-line ID outputs. So here in this paper, we kind of try to bridge the gap between identification and estimation and try to pave the way for developing better estimators for these functionals like semi-parametric RAL estimators. So let's formalize it a bit. Say we have data on treatment T, outcome Y, and some covariates X. They could be pre-treatment, post-treatment, or both. And we have a graph that kind of tells us the story of how these variables are related and how the hidden variables are related to observed variable. So given that, we are interested in the causal effect of T on outcome Y, which is captured by a counterfactual contrast of the form Y parentheses little t, which is the potential outcome Y had treatment T been assigned to little t. We just use potential outcome and counterfactuals interchangeably. So we set our target for simplicity to be just the counterfactual mean. Once we know how to estimate the counterfactual mean, we know how to estimate the ACE. And so the question that we are interested in is just in graphs where this counterfactual mean is identified, how can we estimate that? So we are after estimators with nice properties, like estimators that are consistent, asymptotically normal, estimators that are efficient, that possibly they achieve the semi-parametric Cramer-Rowe bound, and estimators that are possibly robust to model misspecification, which would allow us to use flexible models in our estimation scheme. So here we focus on the effect of a single treatment on a single outcome, but we are thinking of extending it to longitudinal settings with possibly multiple outcomes. So if an appealing class of estimators that satisfy kind of like these properties are semi-parametric RAL estimators. So let me quickly tell you about that. So assume we have a statistical model over a set of random variables V, where gamma here is the parameter space and eta index as a specific model, and we are interested in parameter psi. And psi hat n is an estimator of psi based on n IID copies of V. So we call this estimator to be regular and asymptotically linear if there exists a measurable random function u psi that is mean zero and has a finite variance, such that we can write down the difference between the estimator and the parameter in this form as a function of u psi plus a term that goes to 0 in probability as n goes to infinity. So this u psi is called the influence function, and by simple consequence of central limit theorem and Slotsky's theorem, we can show that this estimator is consistent and asymptotically normal, and as the asymptotic variance of the estimator is going to be the variance of the influence function. So influence functions are important, and one way of deriving them is through what's called a pathwise derivative. So we consider a finite dimensional parametric submodel that contains the truth, and it can be shown that the derivative of the parameter in the parametric submodel evaluated at truth is going to be equal to the expected value of the influence function times the score, where expectation is taken with respect to the truth, and the score is just the derivative of the log likelihood. So this representation kind of gives us a very straightforward way of deriving influence functions. So we also know that in non-parametric saturated model, a model that where the score function is unrestricted, the influence function is a unique influence function. So as we place more and more restrictions on the tangent on the score function, the class of influence functions will grow bigger and bigger. And it's known that the class of all influence functions is basically, if you know one influence function, it is easy to construct a class of all of them if you know how to derive the orthogonal complement of the tangent space, where the tangent space is basically the space spanned by the score. Why we care about the class of all influence functions? Because this yields the class of all RAL estimators. And in this class, there is one influence function that achieves the semi-parametric efficiency bound, which yields an estimator with the lowest variance. And what is that? It's the unique element in the tangent space, and how do we obtain it is by projecting an influence function of choice onto the tangent space. And usually this influence function is the one that we derive using the pathwise derivative scheme, right? So to reiterate our objective one more time, is we want to construct RAL estimators for our target parameter, the counterfactual mean, in a model where the parameter is identified, is non-parametrically identified. And we want to kind of work with models that are representable via graphs. And of course, we are allowing for unmeasured random variables. So let me quickly tell you about a simple form of graphs called directed acyclic graphs, or DAGs for short. So DAGs are pretty great. They are extensively used to kind of like to represent the causal relations, and they also have helped researchers across multiple disciplines to kind of communicate their assumptions in a very concise and pictorial form. And a statistical model of a DAG is the set of distributions that factorize as follows: is the product over conditional densities of each variable, each vertex on the graph, given the parents of the vertex, where the parents are basically the vertices that directly point to the vertex. And so the absence of an edge in a DAG corresponds to, between two vertices, corresponds to a conditional independence statement. So for example, if X and Y given, so we can read of these independencies also from the graph by what is called this d-separation. So basically, if X and Y is d-separated given Z in the graph, we can conclude that X and Y is independent given C in the distribution. I'm not going to tell you about d-separation. It's not really key to this talk. And the causal model of a DAG really can be defined over the set of a model over the set of counterfactuals, where counterfactuals can alternatively also can be viewed as being determined by a set of structural equations. So here, the joint distribution over the counterfactuals, where we intervene on the treatment T, is going to be identified by what's known as G formula. And it's very much similar to the DAG factorization, except the fact that this product is excluding the treatment T and is being evaluated at T equals to little t. So basically, that's why like G formula also can be viewed as like truncating or just dropping the term, the density of T given its parents, which also known as propensity score. All right, so as I said, DAGs are cool. One reason is that the target, the counterfactual mean, is always going to be identified via this simple this simple formula. So basically, which is just summing out everything excluding T from G formula. And indeed, there exists an adjustment set in DAGs, and it turns out that parents of T is a sufficient adjustment set that we can use. And once we have an adjustment set, we can basically like use all the cool stuff in the literature, like IPW, G formula, augmented IPW, TMLE, yeah, you name it. And so the thing is, if the DAG is complete, meaning that if each vertex is pointing to every other vertex, meaning that there is no conditional independence statements, then the augmented IPW is going to achieve the semi-parametric efficiency bound. And so in a sparse DAG, we can exploit the conditional independence statements to drive the most efficient estimator by driving the tangent space and projecting the influence function onto the tangent space. So basically, Rodnitsky and Smuckler in their recent paper kind of use this, and you can check it out. So, but really DAGs are too good to be true. So the more realistic setting is where we have unmeasured confounders. So consider these two hidden variable DAGs, where the left one is from the first slide where I chopped off the head. So this one, basically, it is worthwhile noting that the set of these two hidden variable DAGs impose the same set of restrictions on the distribution of the observed part of the graph, like T, M, L, and Y. And in fact, we can construct infinitely many such hidden variable DAGs that kind of impose the same set of restrictions on the observed portion of the graph. So it is kind of like annoying, but one nice thing is that we can kind of, without loss of generality, condense all of them, summarize all of them into what's called as acyclic directed mixed graph. So this ADMG here is basically the summary of these two hidden variable DAGs. So an ADMG kind of contains two types of edges, one that are like directed blue edges and one that are bidirected red edges. And there is like a way of constructing ADMGs using the underlying hidden variable DAG, using what's called the latent projection operator that was developed by Verma and Pearl back in the 90s. And here we provided the construction for the sake of completeness, but really for the sake of this, for the purpose of this talk, it suffices for you to just think of, to do a mental replacement and think of these bidirected edges as a hidden variable that is pointing to kind of like both endpoints vertices. Like for example, the bidirected edge between M and Y, you can think of it as a hidden variable that is pointing to Y and pointing to M. And the thing is that the effect, or the counterfactual mean, is identified in the ADMG if and only if it is identified in all the hidden variable DAGs that have the same latent projection that leads to this ADMG. So this kind of like reassuring, because you don't need to worry about situations like, oh, what if the effect is identified in the ADMG, but it might not be identified in the hidden variable DAG, or vice versa. So this situation never gonna happen. So that's why like ADMGs is just a cool summary of hidden variable DAGs. So now that we have this summary, this ADMG, we want to know how can we factorize this. So it turns out this bidirected paths are important in factorization of ADMGs. So each bidirected connected component is called a district. And districts of an ADMG really partitions the vertices into distinct subsets. And we denote the set of all districts with calligraphy D. So Tian proposed a factorization of ADMGs. He said that P of V can be factorized as a product over all the districts in the graph of conditional factors of each district given parents of the district. So this factorization very much is similar to what we saw in DAGS, except the fact that these are these are Qs, not Ps, meaning that these objects, which are called kernels or Tian factors, are not necessarily ordinary conditional densities. So they have nice statistical and causal interpretation. So the statistical interpretation of these factors is that they map the values of parents of the district to normalize densities over the variables in the district. So with this, we basically can treat them as a regular conditional distribution and do all the and apply all the probabilistic operations like marginalization, chain ruling, and all of those. And the causal interpretation of these factors is that they correspond to a post-interventional distribution where all variables outside the district are intervened on. So when are these Qs equals to Ps? The answer is in DAGs, because in DAGs, each vertex is basically a singleton district, right? So we need kind of like to rewrite these Qs in terms of Ps. That would make life much easier. So in order to do so, we need another piece of definition called the Markov blanket, which has been around in the literature of graphs for a long time. And it's defined as the Markov blanket of a vertex Vi is defined as the district of Vi and the parents of the district. So it turns out really we don't care about the entire Markov blanket. We only care about a subset of it, specifically a subset of the Markov blanket that precedes Vi, the vertex Vi, according to a valid topological order. So what is a valid topological order? It's an ordering on the vertices on the graph where no vertex later in the order is an ancestor of a vertex earlier in the order. So because we don't need necessarily all of Markov blanket and we care about this subset a lot, we give it a special name. So why not go with like another bedding object that is smaller than a blanket? We call it the pillow, so a Markov pillow of Vi. And based on this, we can just rewrite the Tian factors as a product of conditional densities of each vertex in the district given Markov pillow of that vertex. Okay, and combining this with the Tian factorization in the previous slide, we can basically have a topological factorization as a product over all the vertices in the graph given its Markov pillow. All right. So to just make it more concrete, let's go over a very simple example here. Consider this ADMG. We can see what the districts are the singleton T, the singleton L, and M and Y together because they are bidirectly connected. And so the Tian factorization, as we said, is a product over the kernels. So it's the kernel of T given parents of T, which is MT, kernel over L given parents of L, which is M, and a kernel over M and Y together because they are one district given parents of the district, which is T and L. So if you want to rewrite this in terms of P's, we need to impose a topological order. It turns out in this simple example, there's only one valid topological order, where T comes before M, M comes before N, and L comes before I. And according to this topological order, we can just write down the topological factorization as P of T given its Markov pillow, which is MT, P of L given M, and P of, we can write down this Q object as a product of two things. One, P of M given its Markov pillow, which is T, and Y given its Markov pillow, which is everything. All right. So now we have equipped you with all the tools that is necessary to just like dive into the main results in our paper. So we kind of like, we divide the class of all ADMGs into 3 classes. Based on some simple graphical criteria, really, that looks at how the treatment is related to its descendant and its children. So on the left branch and the middle branch, the effect is always going to be identified, and we call these graphical criteria adjustment fixability and primal fixability. And on the right branch, the effect sometimes is not identified. And if the effect is identified, is non-parametrically identified, we term the graphical criteria nested fixability. Okay, so let me start with adjustment fixability. Adjustment fixability is a very simple graphical criteria. It basically says that the treatment is adjustment fixability or adjustment fixable or a-fixable if there is no directed and bidirected path to any of its descendant, right? So under this condition, if T is a-fixable, then we showed that the counterfactual mean or our target is going to be identified via covariate adjustment, where the adjustment set is simply the Markov pillow of the treatment according to a topological order. So that this is the simple identification functional for the counterfactual mean. And as I said before, once we have an adjustment set, we can basically like rely on the existing results and just use a nice estimator like Augmented IPW to estimate the effect where the treatment is adjustment fixable, which is doubly robust in correct specification either of the propensity score P of T given Markov pillow of T or the outcome regression of Y given Markov pillow of T. All right. So as I said, like adjustment fixability is a very simple but powerful criterion. So let's say we are interested in the effect of T on Y in this complicated looking ADMG. And we immediately can see that treatment here is adjustment fixable. Why is that? Because district of T is just Z1 and T, because this is the only thing that is bidirectly connected to T. And descendant of T are T, M, Y, D1, and D2. And the intersection of these two is just T, which implies that T doesn't have a directed path and a bidirected path to any of its descendants. So that's why T is adjustment fixable here. And given this topological order, the Markov pillow of T is just going to be C1, C2, Z1, and Z2. And once we identify that, we can just simply use Augmented IPW to estimate the effect of T on Y in this ADMG. All right. So you may wonder why I told you about Augmented IPW. Many of you already know about it. But the thing is, really, on the first sight, it's not obvious that we can simply use Augmented IPW on a big class of ADMGs without going really through the hardship of deriving influence functions. And the other thing is that now we have a very simple candidate, which is the influence function that corresponds to the Augmented IPW that we can work with to get the efficient estimator through projection, right? So let's talk about efficiency. So to deal with efficiency, we need to understand the restrictions on the tangent space. So in ADMGs, there are two kinds of restrictions. One is regular conditional independencies of just X is independent of Y given Z. And the other one is called generalized conditional independencies, also known as Verma constraints. Let me just explain this via an example. Here in this ADMG, we can see that T is marginally dependent on Y, and there is no conditioning set that would make T be independent of Y. How do I know that? It's just we can just read off conditional independencies on ADMGs by what's known as M separation. It's generalization of D separation that I mentioned on DAGS. And I'm not gonna explain the M separation, but I appreciate if you just trust me that yeah, this is the case here. But now if I just divide the distribution of T, M, L, and Y by the density of L given T and M, and obtain a kernel here, then T suddenly becomes independent of Y. So this is kind of like mind-blowing, and this kind of constraint is called Verma because he was really the first to kind of like point out these constraints. So the first step in deriving efficient estimators is to just understand how the tangent space is restricted, or when the tangent space is restricted. But it's complicated because unlike DAGs, absence of an edge in an ADMG may or may not correspond to a constraint. So basically the topological factorization that we mentioned earlier is not gonna capture all of these assumptions. Sometimes it's not even gonna capture all the regular conditional independencies. So it makes life very hard in order to kind of like know what the constraints are. We have an algorithm in the paper that kind of like checks the non-parametric saturation status of ADMGs. It's a very simple algorithm. It's a sound and complete algorithm, and it's gonna just I'm not gonna explain it really, but you can just mechanically apply it and get a yes or no question. So if it spits out yes, it means that the ADMG is going to be non-parametric saturated, which means that the augmented IPW that we just talked about is going to be the most efficient estimator. And if it spits out no, it means that the model is not non-parametric saturated and there are restrictions on the tangent space. But really the thing is incorporating Verma constraints on deriving tangent spaces is not as easy as it may sound. And I haven't really seen a single work that goes through the derivation of tangent space by incorporating these kind of constraints. But we don't give up on efficiency yet. So we just try to set Verma constraints on the side for now. And we are really willing to, we are very excited, we are very interested to kind of solve this open problem, but we set it aside for now. And we try to characterize like a class of ADMGs where constraints kind of like look like regular conditional independencies. As one such class we call Markov blanket shielded ADMGs, which is basically says that if two vertices are not adjacent, then it is the case that neither of them are in each other's Markov blanket. So in these MB shielded ADMGs, the constraints look like this. So each vertex is independent of everything that precedes it, conditioned on the Markov pillow of VI, excluding the things that are actually like conditional, right? So taking these sets of constraints into account in deriving the tangent space, so we derive the tangent space and we try to project out the augmented IPW onto this tangent space. And this is the efficient influence function that we get. So there are nice things in this, this term. The first thing is that really the only the IPW term in the augmented IPW is important. It's important and it helps with the efficiency really. And the projection looks like expected value of IPW given each vertex and its Markov pillow minus expected value of the IPW given only the Markov pillow. And the other thing is that really not all the vertices on the ADMG is going to contribute to the efficient influence function. So basically this is not over all V, it's just a restricted set. So what are the things that what are the vertices that don't kind of add anything to the efficient influence function? One is just a treatment. The other set is the set Z that satisfies these conditions, which inverse are just basically the conditions that the vertices that kind of like satisfy the conditions similar to conditional instrumental variables. And the set D are basically all the irrelevant vertices, like the descendant of the outcome, for example, plus other things that satisfy this condition. So for those who are familiar with Rudnitsky's and Smuckler's work, this may look familiar, and it shouldn't be surprising, because really DAGs are special cases of ADMGs, and yeah, and really treatment is adjustment fixable in DAGs. So this is just like it's going to be the efficient influence function in DAGs. And with that, hand it to Rohit.
Are there questions so far?
Doesn't seem to.
Okay, so I'll go ahead. Thanks, Razieh. Okay, so Razieh just told you about adjustment fixability, which is it's a nice simple criterion. It covers an enormous class of ADMGs, but it doesn't cover every ADMG where the effect of the treatment on the outcome is identified. So now we're going to talk about a slightly more general condition that is also quite simple, but covers a wider class. So if you look at this ADMG right here, it turns out that the treatment is not adjustment fixable. Why? Because of this bidirected path from T to L, and L being a descendant of T. However, what is true in this ADMG is that there is no bidirected path from T to any of its direct children. So the direct children of T in this ADMG are M and Y, and you can check that there's no bidirected path from T to either of these vertices. So we call this condition primal fixability, and it's just a more general condition than a-fixability, saying that the treatment should not have a bidirected path to any of its children in the graph, right? And what Jin Tian and Yuda Pearl showed in 2002 was that this criterion actually coincides with a situation where the post-intervention distribution PVT, so that's the counterfactual distribution where you've intervened on T and you're interested in the effect of T on every other variable in the graph, is always identified. And in particular, it's identified like so. You take the observed data distribution and you divide by what looks like a propensity score. So it's some conditional distribution of T given its Markov blanket. However, it's derived from a kernel. It's not an ordinary conditional density all the time. So in particular, it's obtained from the kernel where you intervene on everything outside of the district of T. So dt here, dt here is just shorthand for the district of T. And so what we do is we try to make an explicit connection with the Tian factorization. And if you look at it, what you see is that if you expand out the Tian factorization of the observed data distribution and divide it by this propensity score, so here are the Tian factors that correspond to everything that's not involved in the district of T, so those remain unchanged. But if I just hone in on the kernel that corresponds to the district of T and just chain rule it, you'll see that you drop the factor corresponding to T given its Markov blanket within that kernel. So really you can think of this identification formula as truncated Tian factorization or nested G formula, if you're a fan of G formula. Okay, so what does this give us? Clearly this sort of hints towards some sort of IPW estimator. So in particular, under p-fixability of the treatment, we have that the target is can be estimated using an expectation of what we call beta primal, where beta primal looks exactly like IPW, except you're using this this nested propensity score, right? However, it's not very useful for us to tell you that this is some propensity score obtained from a post-intervention distribution. We need to tell you how you can actually identify this from observed data, right? So recall by the topological factorization that this kernel of the district of T given its parents is actually a product of ordinary conditional factors of each vertex in the district given its Markov pillow. So that's what this is. And then if you apply some algebra, what you end up with is that under the p-fixability of the treatment, the target is given like so. So replacing this nested propensity score with its identifying functional, we'll see that it's actually a ratio of a product of conditionals. So what's in this product? In the denominator, we go over all vertices that are in the district of T and are also descendants of the treatment in the graph. And then look at the conditional distribution of this vertex given its Markov pillow. So it's just a product of these kinds of conditionals. And in the numerator, you have the exact same conditionals, except you marginalize over the treatment in the numerator. Okay, so that may sound a little abstract. Let's make it concrete with an example. So this looks very much like some of the motivating examples that Razieh was using, except I made this T and C edge to correspond to an unmeasured confounder. So in this graph, the district of T is T, L, and C. And the descendants that are also in the district of T are just T and L, right? Because by convention, T is a descendant of itself. And so what that gives us is the primal IPW for the target is represented like this. So in the denominator, we have P of the conditional density for P of T given C, and L given T, M, and C. And in the numerator, you have a sum over the same product. And if you wanted to estimate this from finite samples, what you would do is essentially estimate these conditional densities, plug them in, and empirically evaluate this outer expectation. And I guess for these conditional densities, you could use logistic regression or whatever is appropriate for the given setting that you're dealing with. Okay, so now we have one estimator, and we know that this is an IPW kind of looking estimator, but we know in augmented IPW, there's another kind, which is the outcome regression. So Razieh and I asked, like, is there another kind of estimator under p-fixability that uses a different set of models from what we just used for primal IPW? And it turns out what we landed on is what we call the dual IPW. And we call it primal and dual, with paying tribute to the optimization literature, because there's primal and dual optimization offering different views on the same problem. So if I were to define this set, the inverse Markov pillow of T, so the inverse Markov pillow of the treatment is all vertices on the graph that are not in the district of T, but have the treatment in their Markov pillow. Okay, so this is already kind of promising because you're starting to use stuff that's not in the district of T. The primal IPW was all about stuff in the district of T. And it turns out that under p-fixability of the treatment, an alternative way of expressing and estimating the target is to use the expected value of beta dual, where beta dual is, again, it's a ratio of things, and it looks like a very strange ratio, where in the numerator, you have a product over conditionals again, but this time over vertices that are in the inverse Markov pillow of T, and this vertex given its Markov pillow, but you evaluate this conditional at the assignment value that you're interested in, so at T is equal to little t. And in the denominator, you have the exact same product, but you evaluate it at the natural value of T. And what we were super excited to see after we thought about it a little more as to why this works, is that really this can be viewed as a probabilistic formalization of the treatment splitting operation in single world intervention graphs, for those of you who are familiar with swigs. If you're not familiar, let's just look at an example and see what that means. So on the left-hand side, I have the same graph, and this is just the observed data distribution. It turns out that the inverse Markov pillow of T here is just M and Y, because these are the things that are not in the district of T. However, T is in the Markov pillow of M due to this directed edge, and T is also in the Markov pillow of Y due to this directed edge from T to Y. Okay, so when you multiply this observed data distribution with the dual weights that we spoke about in the previous slide, what you end up at is this sort of, is basically the swig where you split the treatment node. So you can see that there's a random portion of the treatment node and a portion of the treatment node that's now fixed at the value that you're interested in on intervening to. or assigning the treatment to. And this random node inherits all of the incoming edges from the original graph, and the intervened on node inherits all the outgoing edges, with the result that all of the descendants of this fixed node are now counterfactuals. So as if you've intervened on T. So that offers kind of a nice interpretation of why dual IPW looks the way that it does. And just to make things more concrete, the estimator for dual IPW for this graph is like so. You'll notice that we're using conditionals for M given T and C, as well as the outcome given its Markov pillow. It's possible to just simply avoid modeling the conditional density for the outcome, because it's quite easy to see that this dual IPW is exactly equivalent to if you just took the conditional expectation with respect to Y given T, M, L, and C, and just replace that with the expected value of the outcome given its Markov pillow. Okay, so now that we have two kinds of estimators that seem to be promising in that they use, before I go into that, I also wanted to point out that in dual IPW, notice that there's no indicator being used, and so it uses data more efficiently than primal IPW. It doesn't throw away certain rows of your data. Okay. So now that we've established primal IPW seem to be using different sets of models, let's formalize what that means. So here's the original graph again. And then based off of the topological factorization that Razieh described, here's the factorization of the observed law of this graph. It's just P of C, T given C, M given T and C, and so on. And color-coded here, I've written down the primal estimator for the effect of the treatment on outcome and the dual estimator. And what it turns out that the models that are used in each of these estimators are always variationally independent pieces of the joint likelihood. So the primal uses T given C, and L given T, M, and C, and the dual uses M given T and C, Y given T, M, L, and C, and these are just variationally independent pieces of this joint. Okay, so this sort of raises the question, can we form a single estimator that combines both of these and has the double robustness properties that's similar to augmented IPW? So using semiparametric theory, of course, we took the pathwise derivative of the truncated Tian factorization and derived what we call augmented primal IPW. So in order to explain that, let's define some sets. So just define a valid topological order on V and partition the vertices of the graph into the following three sets. C, which is all vertices that are essentially pre-treatment variables, so ones that come before the treatment in the topological order. L, which is essentially post-treatment variables that are also in the district of T. And M, which is just everything else, which is post-treatment variables that are not in the district of T. And this theorem here, I'm not going to go through all of this math, but it's just here to show you that you can mechanically derive the non-parametric influence function for the target under P-fixability using these three sets. What's important to note from this is that this influence function is linear in the target psi t, so you can see that the target parameter just shows up as a linear function over here. And instead of going over this one by one, I'm actually just going to provide some intuition for how this came about. So just recall that these are the sets that we're dealing with. You can abstractly think of that non-parametric influence function as, so there's going to be a contribution from each vertex in the graph when you take the pathwise derivative. So for each vertex, you end up with some functional that is a function of stuff that precedes this vertex in the topological order, times other stuff, times another functional where you have, that's a function of things preceding VI and including VI. And basically, F2 is not super interesting. It's essentially a product over stuff in the future of VI and then you just sum it out. And then you subtract off a conditional expectation with respect to VI given as Markov pillow. So we're going to focus on this F1 term because that's the most interesting part of this influence function. So F1 is different depending on which of these sets that we partitioned the vertices on the graph belong to. So if the vertex belongs to M, it turns out that F1 is essentially the primal weights had you been interested in VI as the outcome instead of Y. So if you just treated VI as your outcome, these are essentially what look like the primal weights. You may be wondering what happened to the numerator. The numerator is actually just absorbed into the F2 term. If the vertex is in L, it turns out F1 is just essentially the dual weights, as if you had treated VI as the outcome again. And if VI is in C, F1 is just 1, because if you're interested in the effect of the treatment on something that's pre-treatment, it's just going to be the thing itself, right? So it makes sense that the weights are just 1. Okay, so this is just saying that these weights resemble the ones that we've used in beta primal and beta dual if the outcome for VI. Okay, so the estimator that you obtain by solving this estimating equation is doubly robust. But it's not doubly robust in the typical sense that we think of it. It's consistent if you specify two sets of models, one of two sets of models correctly. So our estimator is consistent if either all models involving vertices in M, so the conditionals of Mi given as Markov pillow, are correctly specified, or all of the models in vertices of L, so Li given Markov pillow of Li, are correctly specified. And this statement of double robustness that we've provided in these slides is somewhat conservative. It turns out that sometimes simplifications to the influence function are possible, but because we don't yet have a general theory of how that works, we're just going to skip over that. But there are some interesting simplifications provided in the paper for a few examples. Okay, so to make things more concrete, the non-parametric influence function for the target parameter for this graph is given as follows. Again, it's just mechanically derived using the theorems in the paper. However, what's really important to note is that highlighted in orange here is the primal IPW, and highlighted in purple is the dual IPW. So it's interesting that the primal and the dual, and probably intuitive, that these two estimators appear independently in the non-parametric influence function. And this will always happen when the treatment is p-fixable. And this estimator is doubly robust in two sets of models, the sets being M given T and C, and Y given T, M, L, and C, or T given C, and L given T, M, and C. Cool. So as a statistician, you're probably looking at this and saying, wow, if I have a large graph, this augmented primal IPW thing seems cool, but it may require modeling many, many conditional densities. And we tried having an answer for that. So instead of using the non-parametric influence function as we stated it, you can also use a different restatement of the non-parametric IF that we provide. So when T is p-fixable, you can equivalently express the non-parametric influence function as follows. So again, separating out vertices into sets M and L. So if you're a vertex in M, it turns out that you first obtain estimates for each of your samples of beta primal, treat that as a random variable, and take the conditional expectation of beta primal given all vertices that precede Mi, including Mi, and then subtract off a conditional expectation of essentially the same thing, but exclude Mi from past the conditioning bar here. So just all vertices preceding Mi. And then quite naturally, if you're a vertex in L, you do the same thing, but you do it with respect to beta dual instead of beta primal. So conditional expectation of beta dual given everything preceding Li, including Li, minus conditional expectation of beta dual given everything preceding Li. And then for terms that are in C, you're allowed to use, it turns out, it's equivalent to use either beta primal or dual in order to calculate the conditional expectation. Okay. So what this allows you to do is just fit the conditional densities involved in beta primal and dual, and then just rely on flexible regressions for each of these conditional expectations that show up here. So you could use GAMs or non-parametric kernel regression, etc. And another upshot of this is that the efficient influence function, when we can derive it, is also going to look very, very similar to what we just presented. So let's get into the efficient augmented primal IPW. So recall that Razieh said when an ADMG is Markov blanket shielded, the restrictions on the tangent space look, they resemble those of a DAG. And so under these conditions, so when the ADMG is Markov blanket shielded, we derive the efficient influence function for augmented primal IPW, and it looks almost the same as what we presented on the previous slide. So when T is p-fixable and the graph is MB shielded, these conditional expectations now, instead of taking it with respect to, instead of conditioning on everything in the past of MI, you now only condition on MI and its Markov pillow. And then similarly over here, you don't use everything pre-MI, you just use the Markov pillow of MI. And similar replacements everywhere. Just replace all of the past with just the Markov pillow. Cool. So so p-fixability and a-fixability covers a wide class of models that are quite popular in the literature. So for example, front door itself falls under the criterion of p-fixability. However, again, our goal was to provide estimators for any identified target, for any situation in which the target is identified when you represent your observed data distribution as an ADMG. So consider this graph right here. It turns out that T is not a-fixable or p-fixable because of this bidirected path here from T to R2 to Z to R1, and R1 being a direct child of T. So that violates the condition of p-fixability that we require. However, if you query one-line ID or any of the other identification algorithms that are sound and complete, they will tell you that psi T is identified. So what do we do in this setting? So we came out with what's called the nested IPW with tribute to the nested Markov model of ADMGs, because that's really where this comes from. So even though the observed data distribution that we were given contains these bidirected edges that serve as a hindrance really to estimating the target that we want, we can sort of imagine trying to get to a distribution where these bidirected edges are just missing. We try to vanish them away. And it turns out that we can arrive at such a distribution, and we'll call this P dagger V. And it's obtained from the observed data distribution by some sort of rebalancing operations of using weights involving R1 and R2 really. So this looks a little bit intimidating, but let's just walk through it. So this ratio here is actually is a ratio dedicated to rebalancing R1. So in the denominator, what happens is that it's just a simple conditional of R1 given its Markov pillow. So it's R1 given T and Z. We divide that away, and then we re-multiply by this strange distribution here. And it looks strange because it's actually a post-intervention distribution. In particular, it's a post-intervention distribution where we've intervened on everything outside of R1. And similarly, for R2, we have this ratio here, where in the denominator, again, it's just R2 given its Markov pillow. So we divide that away. And then we're interested in a post-intervention distribution where we intervene on everything outside of R2. What's interesting here is that notice that R2 is just parentless. It has no parents in this graph. So a post-intervention distribution for where you intervene on everything outside of R2 is just the marginal P of R2, because there's nothing to intervene on upstairs. Okay, so once we have this P dagger, T is just, it looks a-fixable now because you've essentially deleted all these bidirected edges. So, and then you can get a simple, what we call nested IPW for the target, where it looks very much like IPW. So you use a propensity score for T given its Markov pillow. However, you take expectation with respect to this P dagger over here, as opposed to the original distribution P. Okay. And then we have a general algorithm in order to do such derivations. It's not important to go over that algorithm at the moment, but what I did want to point out is that sometimes this algorithm will fail. This is not a bug, it's a feature, because it turns out that sometimes the target is not identified from observational data, and the failure condition of our nested IPW is exactly the same as one-line ID, so it's sound and complete in that every time the target is identified, we're able to provide an estimator. And then finally, the cool thing is, notice that we said that T is a-fixable. So anytime T is a-fixable in this, in any distribution that you've arrived at, you can always just rely on an augmented IPW style estimator. So here's the augmented IPW style estimator, except again, the expectation is taken with respect to P dagger that we arrived at. So we call this augmented nested IPW. And this theorem is just to say that it's sound and complete and exhibits what we call partial double robustness. So the models that you require in order to obtain P dagger V must be correctly specified. But after that, you're robust to misspecification of this propensity score or the outcome regression once you have P dagger V. So this is kind of cool because this says every time your target is identified, we can always guarantee you at least a partially doubly robust estimator if the treatment is not a-fixable or p-fixable. Okay, so just wrapping up, some of the key takeaways from our paper is the paper itself. We encourage you to go read it, give us all the feedback. We appreciate any feedback that you have. We hope that we've written it in an accessible way, at least in a way that's more accessible than most papers on this topic. And then besides that, so what we've shown you in this presentation is that a-fixability leads immediately to generalized augmented IPW. That's theorem 2 in the paper. P-fixability immediately leads to augmented primal IPW. That's theorems 9 and 11. Algorithm 1 in the paper is sound and complete for determining if there are restrictions on the tangent space. So this is useful if you're doing any sort of influence function based estimators. So as soon as you know you have one influence function and you know that algorithm 1 says it's the model is NPS, you can just say it's the efficient influence function. And then we also give you this definition of Markov blanket shielded ADMGs, which when it holds, the restrictions on the tangent space are DAG-like. This is in lemmas 14, theorems 15 and 16. And then this can be used to project any influence function because we just give you what the tangent space is when the ADMG is Markov blanket shielded. And then under a-fixability and Markov blanket shieldedness, you get efficient GAIPW, that's theorem 17. Under p-fixability and Markov blanket shieldedness, you get efficient augmented primal IPW, theorem 18. And if the target is identified at all non-parametrically, we give you augmented nested IPW, that's theorem 30. So this sounds like a whole lot, and obviously it's quite difficult. It may be quite difficult to implement if you're not used to graphs and semiparametrics. So luckily, all of the above can be done by a computer. And what we're trying to do is develop this package, Ananke, a Python package that we're planning on releasing at the end of the month. It's almost finished, and we'd appreciate any of your feedback. Tell us what you like, don't like about it. Maybe we'll send out an email later giving you a link to the package or how to install it. This year is Jaren, who thank you, Jaren, for a lot of your contributions to Ananke. So with that, we just open it up to questions, and here's just ways to stay in touch with us if you have any other.
That was awesome.
Yeah, fantastic.
Thanks.
Thanks.
I'm speechless. I'm blown away.
Thanks, Dan.
I have a question. So do you have any idea in finite samples how much data is required for some amount of precision relative to the size of the graph?
That's a good question. We currently don't have that. But like as we said, like when we derive the when we show the double robustness property, so as you may know, the bias that we calculate is going to be a product bias, and it's going to be a product over the set of density, the distributions that is involved in beta primal, and the set of densities that are involved in beta dual, and it's just going to be like, yeah, like you're going to get some flexibility because you can use flexible models to kind of like have a product bias that converges to the truth, like as root n, and yeah, other than that, we don't have anything that links it to the size of the graph.
Any other questions or comments, feedback for?
I mean, for me, the hardest part, right, is just my lack of knowledge of all the graphical model rules. So the semi-parametrics I have a better sense about. What is your suggestion about sources that are kind of graphical models for idiots kind of thing, where markup pillows, markup blankets, you know, districts, all that stuff will penetrate my brain?
Well, I think this is the first time markup pillow has been defined, I think, in our paper. But
like you need a new story time.
Yeah, I definitely need a story time. Like, need to like patch all these rules up on my
Hey, we tried to do graph story time, Dan, like a year ago. You showed up to the first meeting.
Yeah, and I was it was too hard for me. I mean, the jargon is just, you know, I guess you feel the same way about semi-parametrics, right?
Well, I do. They don't. They've learned it all.
Yeah.
I had one question, but I can ask you later, I guess, obviously.
So, I mean, is it self-contained? Is this paper self-contained in terms of what you need to know in terms of graphical models?
We try to make it self-contained, but as Rohit said, we are available also to answer your questions.
Okay. Yeah.
I think, so it's yes and no would be my take. I think like there is a bunch of machinery that this paper implicitly uses. I mean, they define everything, but like there is this whole, you have to fix lots of times idea, and that is not obvious, I guess, if you haven't seen that before. Like I think the hard bit about this paper is how do we get identification in general, like in any hidden variable DAG? So we know the answer to that, and we have known the answer to that since 2006. But just because we know the answer doesn't mean it's entirely straightforward. So you have to learn that part, basically. Like you could learn it the way Jin Tian wrote it, or you could learn it the way like we wrote it with Robin, Thomas, and Jamie with the fixing operator, which is kind of what this paper took. And that's going to take a little reading, basically, because it's just complicated, like what you have to do in general, basically. I don't think there's really any dodging that. So I don't know. So it's self-contained in the sense that they explain all of it, but I think it's not like DAGs at all. It's like G-formal you can kind of get very quickly. I don't think it's quite the same here.
Right.
So
I have a bit of a question about something on the pragmatic side of the estimation bit. You said that, so you showed that there's sort of like a restricted set of models that you need to specify in the primal and dual formulations. And you mentioned, I think Rohit mentioned, like you could use kernel regression or whatever you like. So in Ananke or in general, how do you, like it's a bit different from the usual task of like statisticians are used to saying, I know how to, like, I just have to worry about specifying the propensity score and the outcome regression, and they'll use like random forests for one thing and some other thing for another thing. And now you have like all of these things that you have to specify, and like what's the sort of practical guidance of how to do that well?
So currently in Ananke, what we have, we haven't fully implemented all the options, but what we're thinking of going for is that the user specifies at least what they want to do with discrete variables and what they want to do with continuous variables, and that just those are the two like main the main sub classifications. And then after that, we're thinking we allow for how complicated you want your model to be. So like for discrete stuff, do you just want to do logistic or multinomial logistic regression versus BART versus GAMS, and the same for continuous. It's just yeah, we just offer flexibility in like what you want to, how confident do you feel about a logistic regression, and if you don't feel too confident about it, maybe you can up it to something like a GAM.
I see. Yeah. Yeah, that makes sense. I guess like if the user, I guess it's nice if the user can just sort of specify like broad options for classes of variables rather than like a specific model for every specific variable.
Yeah.
In the package, can we learn the structure of ADMG in the package, or should we specify the directed or undirected like edges? So
yeah, so currently you have to specify all of the edges. There's like an interface for building the graph. Structure learning for ADMGs is an open problem because there's no general algorithm for learning Verma constraints and other things of that nature. So if anyone wants to work on structural learning with ADMGs, that would be amazing.
Because it's not uniquely identified, or because there are many possibilities of different graphs?
Oh, it's not just that. I think we don't even know what Markov equivalence is for ADMGs, or nested Markov equivalence rather. Like we don't, for DAGs, we know that two DAGs are equivalent if they have the same set of adjacencies and same set of unshielded colliders. And we have a similar criterion for MAGs, which are slightly more general than DAGs, allows for unmeasured confounding, but we don't have such a thing for ADMGs. Maybe one thing we could do is like incorporate FCI, get a MAG, and then do some sort of estimation on top of that. But yeah.
Okay.
Yeah, you could use like if you have a MAG or a set of MAGs, you could apply your algorithm to each of those, right? Like a MAG is a special case of an ADMG.
Exactly. Yeah.
Any more questions or comments? If there's nothing else, thank you so much to our speakers. That was really great. And our seminar series will continue in 2 Tuesdays from now. Not this Tuesday, but the Tuesday after that with Eli. And so I hope to see you all then. Thank you, everyone, especially Razieh and Rohit.
Thanks, Brian. Thanks, everyone.
Thanks for having us.
Yeah, thank you all so much. This is tremendous.
Thank you.
See ya.
See you.